Okay guys, in this video we're going to look at a third type of probability referred to as an experimental probability. Now up until now we've looked at two types of theoretical probability. First one is just theoretical probability, which just kind of says in a game or an experiment, everything that can happen is just as equally likely to happen. So how many total outcomes are there and how many of them would be favorable for some event we would find the probability of. The other type of theoretical probability that we've explored is a geometric probability. So again, still kind of this idea that given a geometric space, if we were looking at something like a raindrop landing in a field, it's just as equally likely to land in one space where it is in another. So the key word here is with theoretical probability, we assume everything that can happen is just as equally likely to happen as anything else. When we look at experimental probabilities, this is the actual act of conducting an experiment and keeping track of your data. And so you might consider this four-space spinner down here. If I were to say theoretically how likely is it that I hit a blue, well, out of four spaces there's one that's blue. They're all evenly spaced here, so a 1 in 4 chance. But if I actually spin this spinner 20 times, does that mean that exactly 5 out of those 20, 1 out of every 4 spins, has to be a blue? And the fact is, you could spin this thing 20 times and crazy, I think you'd be cheating, but they could all be yellow, which is really, really weird. So when we talk about experimental probability, these are going to be probabilities that are based on repeated trials of a probability experiment. So I want you to underline this word here. The key word here is trials. We're going to do several trials. And it says that the number of trials is the number of times the probability experiment is performed. Each trial in which a favorable outcome occurs is referred to as a success. So we want to kind of look at this word here, a success. And the experimental probability can be used by finding this formula. So let's highlight this here. Basically, we're going to say if we want to know the likelihood that maybe I spin a blue experimentally, we're going to count how many blue successes we had and then divide by however many trials we did total. So you're going to see that this is different from a theoretical probability in that things may not happen equally likely perfectly, but they will, at least if you do this experiment again and again and again and again, tend to approach that theoretical probability here. So let's look at an example where we might conduct an actual experiment here and then say, looking at our actual results, what do we see happening here? What was the experimental probability of something occurring? So looking at this particular experiment, it says each section of the spinner shown has the same area. So theoretically, everything's equally likely to occur. It says the spinner was spun 20 times. The table shows the results. So this is pretty common, of course. When we conduct an experiment, we tend to record the data. We're going to do it in a tabular form. So one thing I want to go ahead and add to my table right off the bat is this. We know that it was 20 times. We're going to write that the total number of trials is equal to 20. And one key word I want to use here is this. This is really going to be what we call our sample space. So the total number of outcomes here, how many of them are favorable or were successes? So looking at this table, the question I want to answer here is, for which color is the experimental probability of stopping on the same, the experimental probability of stopping on the color the same as the theoretical probability? So what we're going to do here is we're going to work out all 4 of our experimental probabilities for red, green, blue, and yellow. And then we're going to look at the theoretical probability. So let's go ahead and do this. We're going to write our experimental probabilities here in this left column, and we'll just go ahead and get this set up here. These kind of are easier, I think, to analyze when you have the data. So probability of red, probability of green being a success or favorable, probability of blue. Blues are favorable outcomes in this one, and then probability of a yellow here. And so when we look at these experimental probabilities, remember what I had mentioned here, the total number of trials is going to be considered what we call our sample space. So we say, out of these 20 trials, out of 20 times, each time I did this, how many were successfully, say, red? So in this case, I think it'd be fitting if I put that one in red, so I had to do that there. 5 out of 20, and we should, if possible, reduce this if at all possible. So we got a 1 in 4 chance. We could also list this as a decimal. We could also list this as a percent. For now, what I'm going to do is just kind of chase after our decimal. It's going to make it easier to compare our probabilities. So how many were successfully green? Well, we had 9 out of 20 here. If we grab our calculator and we take 9 divided by 20, what we're going to see is this 0.45. So we're going to convert this to 0.45 exactly. Put a box around that there. For blue, we had 3 out of 20, and yellow was equally likely as blue experimentally. So 3 out of 20 here. If we divide that out, we should get 15%. So we're going to divide this out here, but there's our 0.15, 0.15, and then this would also be 0.15. So the question we're trying to answer is, out of all of these experimental probabilities, which one has the same thing as what its theoretical probability would have been? And so I want you to think about this. Which one of these would be what you would expect it to be? And in terms of what we look at here, well, we had 4 spaces. And so the likelihood that I spin any one of these theoretically would be a 1 in 4 chance. It means that our red is going to have the same experimental probability, or did have the same experimental probability as did its theoretical probability. So I'm going to go ahead and list our theoretical probabilities in another column here, just so that we have them. But I really want you to see the difference here. When I say what's the theoretical probability of spinning a red, this assumes everybody's just as equally likely to occur as anything else. So we're ignoring this data set here, saying I didn't do an experiment. How likely is it that I land on red? You know, it's exactly a 1 in 4 chance here. And this is the same pattern we're going to see with our green, blue, and yellow. And again, this is good to write down just because it really drives home the fact that when we talk about theoretical types of probabilities, these are these probabilities that we assume everything is just as equally likely to occur as anything else. So to write a conclusion sentence here, let's go ahead and write a sentence. We would say the experimental probability of landing on red was the same as its theoretical probability of occurring. Okay, so the difference here being, one is based on data, so maybe not as equally likely as we would hope it to be, and the other one is based on assuming everything's equally likely. One more note that I want to make sure we put here is going to pertain to the experimental compared to the theoretical, and it's going to be this. It's the law of large numbers. I want you to write this down. And this basically states that as an experiment is completed a very large number of times, the experimental probability will eventually approach the theoretical probability. Okay, so the idea here is, if I do this experiment enough times, if I do it out of 10,000 times, you know, I may have 2,400 of them be red, which is still not exactly a fourth of 10,000, but 2,400 divided by 10,000, just to kind of give you an idea here, 2,400 divided by 10,000, as our number of trials gets sufficiently large, you start to see this get really close to the theoretical probability of happening. So when we talk about what's a theoretical probability good for, you know, it's not going to be exactly how the experiment's going to go, but if you're a betting person, you probably should bet that it's going to turn out somewhat close to what we assume the theoretical probability would be. Okay, so we're going to look at one more example here, not including a game of chance, but more along the lines of looking at what if we had collected some data based on something we were interested in. So maybe U.S. adults with pets. And so another type of experimental probability you'll see is not based on a table, but based on maybe a histogram, a bar graph here. And so we'll read this. It says, in the United States, a survey of 2,184 adults ages 18 and over found that 1,328 of them have at least one pet. So the types of pets these adults have are shown in the figure. What's the probability that a pet-owning adult chosen at random has a dog? So first things first, what I want to do is underline this word right here. And you know, if I hadn't been told this to begin with, I would want to immediately just come down here and say, well, how many total people are in this sample? So we're going to write total. The total here is 2184, and this is in people. But again, we're going to make a note here. This is what we would consider to be our sample space. The total number of outcomes was these people, were these people. The question we're trying to answer is the probability that a pet-owning adult chosen at random has a dog. Okay, so we're going to write, first of all, symbolically our probability. Probability owns a dog. Okay, so we always want to write this symbolically first. Well, how likely would this be out of the 2,184 people? How many of them successfully own a dog here? And we were able to count that overwhelmingly more people own a dog than any of these other types of pets you see in this graph, but 916 people. So it is very cool to say, well, the likelihood is 916 out of 2,184, and that is intuitively kind of, I don't want to say an obvious thing, but a natural thing to say. However, it's a lot easier to compare these things when you put them in decimal form. So we're going to type in, of course, our 916 divided by 2184, and what we should see is this 0.4194-ish. So we're going to write approximately 0.4194, which I'm going to go ahead and write as also a 41.94% chance of occurring here. So I prefer the decimal. We could also write it as our ratio or our percentage, but this decimal right here is the percentage of people who really own a dog. So if you're going to say, if I choose a person at random, how likely is it they own a dog? It's kind of like saying, well, if 41 and almost 42% of people own a dog, then you got a 42-ish% chance of this occurring, okay? So let's look at this extra example 6 here. It just says, using the same survey data displayed in the example here, what's the probability that a pet-owning adult chosen at random has a bird? So just like we carried this out before, we say, owns a bird would be our favorable outcome here. Out of 2,184 trials of this experiment, how many successfully produced a bird? And so this was our least frequent category here. And looking at this, we should get a probability that's much closer to 0 just because it's not as likely to occur. So 0.2184, we get 0.0426-ish, 0.0426-ish. And that'd be about a 4.26% chance. Okay. So when it comes to looking at experimental probabilities, just know that it's different from the theoretical probability in that if you actually complete the experiment, we're looking at, out of the total number of trials, how many of them produce a successful outcome, which would be what we were previously calling favorable outcomes.